Hello everybody, this is Professor Iris Miano presenting Day 10 lecture on section 3.3. This will be the last section that is covered on the material that will be exhibited on exam 2. So we could call this Unit 2 wrap-up section. And so Unit 2, just to be clear, spans the sections 3.1, 3.4, 3.5, 3.2, A11, 2.7, and of course this 3.3 section that we're covering here. So those are the sections you'll want to make sure you're feeling really good about in regard to exam 2 coming up soon. Okay, so in this section we are going to be talking about complex zeros, what they look like, how to find them, and also the fundamental theorem of algebra. So it's not much new stuff. We just really need to reformulate how we think about polynomial functions and their zeros. So we want to expand that idea to include complex zeros with non-real imaginary parts connected to them. So the definition of complex zeros, leading coefficient, complex polynomial function is reintroduced right over here. I just lifted this from your textbook here, and it just basically reminds us that all of these coefficients in the constant term are indeed complex numbers, even if they are don't have any imaginary parts, because all of the real numbers are also complex numbers, right? So the complex number set, just to be clear, is all of the real numbers, all of the imaginary numbers, all together in one enormous set, okay? So while imaginary and real numbers are disjoint sets compared to one another, collectively they form the complex number set. So when I say talk about real zeros, I'm talking about complex numbers with no imaginary part. And when I talk about complex zeros, generally I am referring to complex zeros with an imaginary part. So I'll try and specify that every single time it's mentioned, but just in case, complex zeros are meant to be non-real numbers when they are referred to. So thinking about polynomial functions that have no real zeros. So this has come up from time to time, and if we want a visual of this, we can think of even-degreed functions with positive leading coefficients in which all the turning points are above the x-axis. So if I wanted to draw a quick pic of what that looks like just real super quick, something like this. Note this pink trajectory here, where you have it going off to positive infinity, and maybe you have some stuff like this, right? And so notice that at no point does this purple magenta E line cross the x-axis, so that means that there's not going to be any real zeros. But there are complex zeros to this, and that's because, excuse me, there's going to be, at the very least, an irreducible quadratic factor associated with the polynomial function being exhibited by this very rough quick drawing that I put on here. So in those irreducible quadratic factors do have solutions, right? They have a solution, and we can get at the solution by using the quadratic formula. So by virtue of that fact, we have the fundamental theorem of algebra. Excuse me. Which was proven by Gauss. It's a Gaussian proof. Excuse me, once again, let me drink some water. But yeah, so you can look that up if you're interested in the mathematical history associated with that. For our purposes, we just need to know this very important theorem in order to justify the endeavor of finding zeros for any polynomial function. Like, that's always a worthwhile endeavor, and it gives you, certain information based on what your polynomial function is supposed to be exhibiting. Excuse me. So this is to say that every complex polynomial function f of x that's not linear, right? Or no, it could be linear actually, excuse me, n could equal 1. So it's got to be linear and not vertical, right? So it's got to be something else. This is how it'll look in its factored form, in which, excuse me, a sub n, r sub 1, r sub 2, and r sub n. So r sub 1 and through r sub n are all the zeros, and then a sub n is the leading coefficient. So all of those are complex numbers. They could be real, they could be non-real. All we know is that they're complex. And so we want to have this theorem extend to all of complex numbers because we want to, having knowledge of how they work and how to arise at complex solutions, we now can add that to the cache of solutions possible to be extracted through our analyses, okay? So, yep. So we're just going to redo all of our previous analyses, but also once we come to some quadratic irreducible factor, we will use the quadratic formula or some such other mechanism to solve that equation set equal to 0 in order to find the non-real complex zeros. So non-real complex zeros always come in pairs, conjugate pairs to be exact. I just kind of read that word for word on accident. That's just how I would describe this. And here is a theorem that says exactly this, is that when you have a complex non-real zero of a plus bi, you can come up with its conjugate, which is just the same exact expression but with the subtraction instead of addition between the real and imaginary parts, in order to find an additional zero, because complex non-real complex zeros always come in conjugate pairs. So the conjugate will give you the other one if you have one of the imaginary zeros. So yes, and then there's a series of theorems that are presented that are already in play for the way that we think about these things, which is to say that if we have a polynomial function of odd degree, what are the possible number of real zeros that we could have? Well, there's definitely one. That's what this theorem is pretty much exhibiting right here. And then depending on the degree, you could have all of them be real, right? Or you could have reductions by 2 numbers as possible values. And then, what else can we say? Right. So every polynomial function with real coefficients can be uniquely factored with linear factors, right? So those binomial factors that we've always seen that are x minus the zeros that we've come across. And then also you could be left with having sifted out all of those real zeros, you could have an irreducible quadratic factor left. And so that's what we'll mainly be focusing on as the new part of the analyses for these sections, depending on what type of example is being asked. Okay, so let's investigate a few examples from the textbook homework set so that we could see how this new stuff comes about. Okay, and I'm going to actually put in a couple of, there we go, what we call it, spaces so that we can see this other complex non-real zero in its whole format. It's not like cut off. Okay, so let's tackle example 1, in which we are going to form a polynomial function f of x. So we don't know what f of x is, but what do we know about it? It has real coefficients having degree 5, and its zeros are 1 with multiplicity 3. So that means right off the bat we could say there's an, in factored form, it would look like x minus 1 quantity raised to the 3rd power. Or, I mean, if you had it expanded out, it'd be x minus 1 times x minus 1 times x minus 1. And then also they give us just one non-real complex zero. So we can use what we just said about complex zeros that are not real always having to come in pairs. to assume that the conjugate is another 0. So let me go ahead and write that down to begin with. Let's see. So yeah, this little bit right here, we'll just say, so another 0 must be 1 minus I. Okay? So keeping that in mind, and then also taking this little piece of information, this means that one of the other little bits of this function is going to be x minus 1 to the third power. That's how you have a 0 of 1, but with multiplicity 3. Okay, so we'll take this information, and this information, and come up with our f of x function. So putting it together initially is kind of a snap. I'm going to go ahead and start with my real zeros. That's supposed to be a 1. Let me make that one a little bit prettier. To the third power. And then here's how you can write your complex zeros. So we have x minus 1 plus I, and then x minus 1 minus I. You could certainly distribute through that negative sign if you feel so inclined. If you want to keep it this way and just focus on, for instance, this little bit, like multiplying this part out, because eventually you're going to have to multiply all of these things together, because when they say form the polynomial function f of x, it's not explicitly stated, but the implication here is that they want it in standard form. So, you know, all of the multiplications need to be addressed, and furthermore, we need to, what's the word I'm looking for? Yeah, have the terms going from highest degree term all the way to the constant term if it exists. So let's go ahead and multiply this through, and we could FOIL right here. Firsts, outers, inners, lasts, and you might get the following. Now you might be able to do this a little bit quicker and easier than I do. I'm just going to show what I perceive to be every single painstaking step in here, just to make it super clear how I'm going to get my final product here of just these two factors that give me my complex conjugate zeros. So this, my firsts are here. Here are my outers. Here are my inners. Oh, sorry. Oops, made an error here. Let me erase some stuff in here. So sorry. Let me wake my brain up a little bit. That's 1 plus I. And an x on the outside. And then my lasts are going to be plus 1 plus I, 1 minus I. So I can rely on a little something that I learned in that A11 section, just reviewing the rules with imaginary numbers in order to deal with this last product right here. Okay, so anyway, what will this become? This will be x squared minus, if we distribute this through, it'll be minus x plus ix. Yep, and then minus x minus ix plus, and then this becomes a 1 plus 1, believe it or not, because you take the a, which is the first thing, and you square it, plus the coefficients of these i's, which will be squared, which is again a 1. So notice that, let me get the red out there, this ix and this subtracted off ix cancel out, and I will be left with x squared minus 2x minus 2. Again, folks might have come to this conclusion a little bit faster with other methods, but this is the method I chose to show you here. Okay, so this multiplies these two complex conjugate as zeros. The binomial functions associated with those multiply to give us this. And then what do we get when we multiply? Oh, sorry, let me go here. This bit right here. Like what is going to be this? Now you can multiply it through in a couple of steps, or you can use Pascal's triangle to get the coefficients. And yeah, so there's this whole thing with Pascal's triangle. So I'll just kind of cut to the chase here and say that this multiplies out to be x to the third power minus 3x squared plus 3x minus 1. Okay, so having that multiplied by this, you're like, oh god, how do I deal with this? I would use an area diagram. Have you guys ever used this before? If not, here you go. If you want to multiply a 3-termed polynomial by a 4-termed polynomial or higher, you can come up with a 3×4 situation and put the terms at the row headers and column headers for each of the two polynomials that you're trying to multiply. So, and make sure signage comes along for the ride. Okay, so if I do that, then I can, in each of the boxes, put the product of their row and column headers. So for instance, this will be x to the 5th power, right? This will be negative 3x to the 4th. This will be 3x to the 3rd. This will be minus x squared, and so on and so forth. So we'll fill out the entire box. You'll find that on the diagonals you're going to have like terms, and that'll help you to get your ultimate final answer here. So just going through the motions of filling out the rest of this box, we'll get negative 2x to the 4th power here, positive 6x to the 3rd. That'll be negative 6x squared and 2x here. Okay, looks like I'm doing good so far. Negative 2x to the 3rd power, 6x squared, negative 6x and 2. Okay. Oh, hold on. Sorry, that's a +2 there. Yikes, I made an error earlier and it looks like it's carried over. So let's erase the negative sign here, and that will change all of the signs. And thank goodness, only this bottom row here. Whew, that could have been disastrous. Let me just go ahead and take out the negative signs there and here, and then put negative signs in there and there. Okay, so as you can see, being careless and rushing through be very detrimental. Okay, so notice on the diagonals here, I'll just kind of circle them. We have like terms, right? Here in this first diagonal, we have 4th degree terms, 3rd degree terms, 2nd degree terms, 1st degree terms, and so on and so forth. So we just add up all the like terms, and you'll get your ultimate final answer. The function that we created in standard form. So that'll be x to the 5th power minus 5x to the 4th plus 11x cubed minus 13x squared plus 8x minus 2. Now this is, answers will vary for a problem such as this, but this is the final answer you should expect if you have a leading coefficient of 1. Okay, cool. So that's that. Example 2. Different kind of problem here. We're going to use the given 0. By that I mean your negative 4i, to find the remaining zeros of the function. Okay, so if negative 4i is a 0, since it is complex and has a non-real part, the conjugate has to also be a 0. So since non-real, 4i, positive 4i also has to be a 0. so what is the factor associated with this 0 right here? So factors that we know have to be included in this polynomial function is x plus 4i. That'll get us this 0 right here. And then also x minus 4i. We'll multiply these together, and you will get x squared plus 16, right? Okay, so if we know that x squared plus 16 has to be itself a factor, okay, then we can use some polynomial long division in order to see what the depressed function of h of x will look like. The depressed function will be q sub 1 of x, right? Remember that notation? In order to just whittle down the function in order to see what the remaining zeros will be. Okay, so again, let me just kind of preemptively kind of circle this. These are the 2 zeros so far that we know of. There's 3 more that we need to glean, okay? They may or may not be real. It's not something we really care about here. We know that we have 2 non-real complex zeros in the bag. One of them was given to us. The other one was fairly obvious based on the complex conjugate pair theorem. Okay, so let's go ahead and bust out some polynomial long division and divide out x squared plus 16 from 3x to the 5th plus 2x to the 4th plus 15x to the 3rd plus 10x squared minus 528x, yikes, minus 352. Whew, we're going to have our work cut out for us here, but we can do it. All right, so you always ask yourself, what do you multiply the first term in your divisor by to get the first term in your dividend? I believe 3x to the 3rd power will do it. It's nice to line up like terms, so I'm going to choose to put the 3x to the 3rd over the 15x to the 3rd. Multiply through, and you'll get 3x to the 5th plus 48x to the 3rd. Lining up like terms is crucial to this process. Notice that I left the x to the 4th area blank. That's on purpose. We're going to, distribute through this negative sign. That's going to turn this into subtraction. We can then drop the parentheses. This eliminates as desired, and we will have, well, this needs to drop down, and we will have 2x to the 4th. And it drops down by virtue of having nothing to subtract it from. Then we perform the subtraction, which will yield a negative 33x to the 3rd. And then you drop down the next term, which is the consequence of the process, okay? So, in fact, I'm going to actually erase this word right here, just to keep this so separate right there. Okay. Now, what else do we do next? Okay. So we ask ourselves, what do we need to multiply the first term in our divisor by, x squared in this case, to get the first term in our new dividend, 2x to the 4th? Well, that'll be a 2x squared. Okay, so that'll come in the next term in our quotient, 2x squared. Multiply through, you get 2x to the 4th plus 32x squared. Okay. Oops, that's supposed to be a 4 right there. Subtract. And several things are happening. This will eliminate by virtue of going here. This now turns into subtraction. Eliminate those things right there. This negative 33x to the 3rd will drop down because nothing is being subtracted from it. This subtraction will yield negative 22x squared. And then we will have this next term drop down as well. Excuse me. Minus 528x. Okay. Again, what's going to be the next term in my quotient? It'll be minus 33x. Multiply through. This is where the numbers get wild, but kind of familiar, right? Because negative 33 times 16 happens to be negative 528x. This is actually working out wildly awesome. Okay, we'll do some adjustments here, distributing through that negative sign here, here, and here. Elimination there is achieved. Drop this down, negative 22x squared. And then this will also eliminate by coincidence. And then we still need to drop down this guy right here, minus 352. Almost done. So the last term in our quotient will be minus 22. Okay, and then we'll distribute through, and you're going to see that it completely eliminates. You get no remainder here as would be desired. Okay, so we're subtracting. Yes, 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 all eliminated. Big fat 0 for the remainder. Cool, cool, cool. Okay, and we knew this because we were told that, again, negative 4i was a 0, so therefore 4i has to be 0, therefore this has to be a factor. So we knew that this process was going to yield a 0 remainder. So now the remaining, the quotient yields the first depressed equation, which is 3x cubed plus 2x squared minus 33x minus 22. Now looking at this with my knowledge of factoring, I see that being a four-termed polynomial with having some structure in the two first terms and the two last terms that are similar, this is going to lend itself nicely to factor by grouping. So put a big plus sign in between here. Okay, so what's the GCF of the first grouping? It's going to be x squared. Then that'll leave with 3x plus 2. And then the GCF of the second grouping will be a negative 11. We'll be left with 3x plus 2. Oh, beautiful. So then that will factor to 3x plus 2 being the common binomial factor, and the leftover bit will be x squared minus 11. Now x squared minus 11 isn't factorable, but it still is going to give us not only zeros, but real zeros. So it'll just be irrational. No big deal. So this is going to give us a 0 of let's see, negative 2/3, if I'm not mistaken. And then when you set this equal to 0, right, you're going to have zeros of positive and negative square root of 11. So just to be clear, so what we're supposed to do here, find all the zeros and rewrite it. Oh, find the remaining zeros. Okay, we don't even need to rewrite it in factored form. Although if they asked us to do that, we would do it, and I believe that's the part of the instructions for the last example. So all zeros are, so they gave us negative 4i. We also were like, hey, 4i has to be in there as well because all real complex zeros have their conjugate as another 0. Just a given, negative 2/3. Negative square root of 11 and positive square root of 11. And that'll do it. I have one more example that I want to present to you. We're going to find all the complex zeros of this last function, polynomial function, and write it in factored form. Now this one was the very last exercise in the textbook homework set, and I wanted to do this because I kind of wanted to show how wild this process can get as far as having like an absurd number of possible zeros that you get, and like how many times you could go through the trial and error. Now, I'm not going to go through the synthetic division of every single thing that I've tried. Like I've done this problem ahead of time. I'm going to let you know which ones I tried, which ones didn't work, and I'll demonstrate the ones that did work as far as the synthetic division is concerned. Then we'll get our what's it called? Depressed equations along the way. And if we, at some point after getting some depressed equations, we can either factor or we're down to at least a non-factorable quadratic, then we can use a quadratic formula in order to find the remaining possibly non-real complex zeros. Okay, but the first thing we want to do here is go through the analysis that we know and love. How many real zeros can we expect? So at most, we can expect 4 real zeros. Sign analysis. And by that I mean the Descartes rule of signs would yield that we have 2 or 0 positive real zeros, two or 0 negative real zeros. I'll leave the work out of it just in the interest of time and focusing on the things that are more pressing. A sub n, the leading coefficient, is going to be 2. The constant term is 65. So that leaves for P and Q lists as follows. So that'll be plus or minus 1, plus or minus 5, plus or minus 13, plus or minus 65. So 8 possible factors for P, yikes, kind of a lot. Whereas Q, it's a much shorter list, plus or minus 1, plus or minus 2. So that gives us a P over Q list of plus or minus 1, plus or minus 5, plus or minus 13, plus or minus 65, and then all of those divided by 2, so plus or minus 1/2, plus or minus 5/2, plus or minus 13/2, and then finally plus or minus 65/2. Yikes, like so many possibilities here. Where do we start? Now you always want to start in the same place. So I'll go trying. So I'm on part 3 now, technically in the process. Trying for x equals 1, 0. I found that that did not work. Okay, so I'll just go ahead and put a red X underneath it. Nope. And then next thing I tried was -1. Because you always want to try the smallest, easiest to work with integers that you can, the ones that are closest to 0. I will tell you, -1 also did not work. Okay, so where did I go after that? I went for 5. 5 worked out. So let me go ahead and show you what 5 looked like. So 5, right? And then the coefficients here would be 2, 1, -35, -113, and 65. So I'm going to give myself some more room here. So that'll be dropping it down here. We get 2, multiply through, we get 10, and 11 is the sum there. It'll be a 55 there. 20 will be the sum there. Bring it around town, and that'll be 100 with a -13 sum. And then 5 times -13 will be -65. Whew, very satisfying. Now, just to be clear, when I tested out, I'm not showing the work for this, but when I tested 1 and -1 as zeros, I went through this process and I got something other than 0 right here. So I'm like, oh gosh, it's not a 0. Keep going, keep going. And so 5 ended up working. So now this yields, not only do we know that 5 is a 0, but we are given the depressed equation. We call it q sub 1 of x. which is 2x to the third power plus 11x squared plus 20x minus 13. So from here, we need to go into a reiteration of what's going on with the P over Q ratio, but we get to really just shave off some things because we have similar numbers to being the leading coefficient, and now it's not 65 as the constant term anymore, but it's 13, which is a factor of 65. So really we could just take off the 65 here, right? Oops, actually, hold on, oh crap. And we just want to maybe just take that off and take this off and this off, and then this list, the remaining stuff in this dark magenta, is going to be the list of possible values. And so the ones that didn't work before, we don't want to retest because they're just not factors at all. But the ones that did work before could work again. However, I chose in the next iteration to not try positive 5 again. In the next step, like from here, trying, what were the next ones that I tried? X equals -5. That did not work. So I'll put a little X over there. Go back to green, I guess. The next one I tried after that was -13. And the numbers just got wildly out of whack. And so I was like, you know what? Maybe I'll scale it back down and I'll try one of these fraction-y numbers, okay? So that's what led me to try 1/2. And I know what you might be thinking, well, why didn't you do the upper lower bound thing here? Well, I tried, my initial 2 values are the ones that you try for the upper and lower bounds, and I'll tell you, I did not get positive values for 1, and I did not get alternating values in those third rows for 1 and -1 respectively. So I would have had to try other larger values in order to get the bounds, and it did not seem to me to be a worthwhile endeavor. It seemed like a waste of my time. I might as well just try other, numbers like I'm going to be doing that anyway in the process of finding the actual zeros. So it did not behoove me. So 1/2 though, I can tell you worked. And let me just show you what the work looks like for that. So if 1/2 is the 0, and remember, use the depressed equation coefficients, which are now 2, 11, 20, and -13. We're going to shove that one down for 2, multiply it through, and to get 1 right here, and then add those to get 12. I know using 1/2 probably feels a little bit scary because you feel like, oh, I'm going to get some fraction numbers in this process. Luckily, though, we do not, because all of the stuff that drops down ends up being even. Not that you would necessarily know that to begin with, but we're very lucky in this way, and nothing got crazy. So then this will be a 13, and then we get a 0. So having a 0 remainder in this synthetic division process yields, a depressed equation, and we know that the 1/2 value, or whatever our value of x is in the proposed 0, is indeed a 0. So that means our q sub 2 of x equals 2x squared plus 12x plus 26. Okay, now trying to factor this, because it's quadratic, we have some options. We could notice that there's a GCF, right? So we could factor out that common factor of 2 and be left with x squared plus 6x plus 13. And then we will check to see if this remaining quadratic in the parentheses here is factorable. Turns out it isn't, so the best thing we could do after that is use the quadratic formula. So that will yield x equals opposite of b plus or minus the square root of b squared minus 4ac all over 2a, which is just a 2 in this case. All right, so simplifying everything down here, we will get the following. So I'm just going to go dot, 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 and under the express understanding that you could simplify this on your own. If you want me to demonstrate in class, I will upon request. You should get -3 plus or minus 2i. Cool. So that's a complex conjugate pair, and so that's 2 solutions right there. And then otherwise, we were able to successfully go through the synthetic division process with 2 real solutions. And remember, there were 4 zeros total. 2 of them at most could have been real, but 4 of them could have been real. Only 2 of them ended up real, and the other 2 were non-real, complex. So here are the zeros. Let me list them. They are 5, 1/2, -3 plus 2i, and -3 minus 2i. And then the factored form of the function is just take all of your zeros and put x minus that 0, right? X minus 5, x minus 1/2. And for these ones that have, operations in them, you could distribute through the subtraction on that and call it x plus 3 minus 2i for this particular 0, and then x plus 3 plus 2i for that last one. And then that will give us everything that we need. Here are our zeros, and here is the function rewritten in factored form as desired. That's it for today. Let's go ahead and talk about whatever you would like regarding 3.3, and then when we're done with that, we'll start reviewing for exam 2. Thank you so much for your attention. See you soon.